Okay, I'm going to start with a quick part of theory that we might need later today. It can be expressed in terms of various Fourier transforms, but let us express it in terms of the fast Fourier transform, which is the finite extent discrete signal domain. Okay. If you had a signal with finite extents, okay, finite extents means that you can imagine it to be a circular signal. Its ends to be connected to each other, and it has some Fourier transform. The Fourier transform is going to be as many numbers, and they could be complex numbers, and each number will describe the amount of a particular spiral, existence of a particular spiral in this signal. Correct? That would be the discrete Fourier transform of this signal. My question is, what will happen if I were to shift the signal right by a certain amount? And let's make it easy. Let's say that we are shifting the signal right by one sample. Okay. Then what will happen to its Fourier transform? Is the question clear? Okay. Now, what do you really mean by shift in this case?
Rotation.
Yeah. Because it's a signal with finite extents, what happens at the edge is important. So when we say shift, what actually happens is that last sample goes and comes back as the first sample. Okay? As if they're playing musical chairs. So, okay? And we could shift by multiple amounts, but right now for simplicity, I'm going to say that it was shifted by one. And the question is, what happens to the Fourier transform?
Doesn't change, right?
Doesn't change? Okay. Two simultaneous votes for doesn't change. Why not?
If we repeat the signal and make it infinite in length, the frequencies of the various things won't change, which compose the signal.
The frequency content won't change is correct, but the amount of frequency that you don't use won't change. The frequencies themselves will not change because that's just dependent on the number. There is something that will change. The starting phase, okay, will change. Why? Because it's decided that the starting phase is going to be anchored to this index. Okay, it's the index, it's the phase or the angle that every spiral has at this index, at index 0. Okay, and so the phase will change, the starting phase will change, the amplitude will not change, the frequencies themselves will not change, but the starting phase will change. Okay, once again, we are discussing the problem of what will happen if in the signal domain I was to shift the signal by one sample, which actually rotates one of the samples back. Okay, so the last sample goes back to the first sample. So it's called a circular shift. And what happens in the frequency domain, correspondingly in the frequency domain. Okay. Anything else that anyone would like to add? What happens in the frequency domain? Nothing should, he's still sticking to nothing should happen. Okay.
So all of the values would be, there would be an addition or a subtraction of a constant value.
There would be a addition or a subtraction of a constant value.
To each sample in the signal, to each sample in the Fourier transform.
Addition or subtraction in what?
In their amplitudes.
Okay.
Shifting in time domain by one sample is just a convolution.
That is one way to look at it actually.
Multiplication in frequency domain.
Yeah, shifting shifting the signal is just a convolution, right? Convolution by what? Convolution by the signal 0, 1, 0, 0, how many over 0, 0? Correct? Yes. So that gives you one hint of what will happen to the Fourier transform. Convolution in the signal domain is going to give you a multiplication in the Fourier domain. And so each number in the Fourier domain, whatever those numbers are, these 6 complex numbers, they will get multiplied by some specific number, some constant maybe, which is going to be related to, which is itself going to be the Fourier transform of this signal, okay, or this convolution kernel. Is that okay? That is one way to think about it. And then you can find the Fourier transform of this, and from that you can figure out what the answer is. I invite you to do that as homework. We'll see a simpler, even more intuitive way of thinking about this, and that is as follows. Just think of some spiral, okay? Let's say it is the spiral that makes one turn in this much period, okay? Remember, there are various spirals and they have to make a integer number of turns, a periodic number of turns in that much period, correct? So if it makes one turn, and there are various such spirals that this is made up out of. Now, if I were to shift it, it would work if I could shift all of these spirals. If I could shift the spirals themselves. Okay. Now, that's an unusual thing to be doing to the spirals. Spirals are supposed to be scaled and rotated. They are not supposed to be shifted. But
Shifting is scaling and rotating.
yes, shifting a spiral is scaling a spiral, right? Or rotating a spiral. Correct? Because of the, principle of the rotated corkscrew or whatever you want to call it, right? A spiral shifted is a spiral rotated. Can't make out the difference. And so, what will happen? So, this spiral now, it starts with 1 at an angle of 0, correct? And then, what will be the next value of this spiral? Let's say it's just the 1 turn spiral. What will be the next value? 1 angle 1 by 6, in general 1 angle 1 by n, okay? And 1 angle 2 by n and so forth, correct? Now, if I shift this to the right, what happens to the phase? Decreases by 1 by n. Okay? The phase goes back by 1 by n. Right? Because it's this last sample, which is 1 at an angle minus 1 by n, which is going to come here. And so the starting phase goes back by 1 by n. Now, this will happen to the spiral regardless of whether it started with 1 angle 0 or it started with some other starting angle. It will always go back by 1 by n. So, the 1 index spiral, which is the 1 frequency spiral, k equal to 1 spiral, is going to go back in phase by 1 by n. Okay? So, what will happen in the Fourier domain as I shift this? Okay? As I shift in the time domain, by 1, what will happen in the Fourier domain is this will get multiplied by 1 angle minus 1 by n. Okay. This is the number telling you the starting phase of the 1 by n spiral or the first spiral. Index 1 spiral, which is the spiral that makes 1 by n turn per sample. And that will get multiplied by this number, 1 angle minus 1 by n. Does this make sense? How much will this get multiplied by? Same. All of them will get multiplied by 1 angle 1 by n. He still wants to minimize his effort. His first answer was there will be no change. Now that one of them is changing, they are all changing by the same. Okay, so
Multiplication by 1 angle minus 1 by n is just subtraction of angular part of the complex number. Magnitude remains same.
yes, correct. That is correct. So the magnitude of this complex number remains the same, and its angle you subtract 1 by n from it, which is basically having the same size of spiral and then going back 1 by n, right? Correct? Okay. Next spiral is what is the 2-turn spiral. It makes 2 turns, right? And then what will happen to it? As I shift it by 1 sample, I am shifting everything by 1 sample. As I shift it by 1 sample, what will happen?
Same thing.
But
N is now different. You had 2n over here. So we are rotating by 1 angle to 2n per sample.
yes.
So it will go back by minus 1 by 2.
Minus 1 by 2n. Okay. Think through this carefully. This is 1 angle 0. This next sample here is what? It's 1 angle 2 by n. Okay? 1 angle 0, 1 angle 2 by n, 1 angle 4 by n, and so forth, so forth. And if it does n of these, it comes back to 1 angle 0. That's the second spiral. So, if I were to rotate this to the right, which means this sample comes here, what is the multiplication by? Minus 2 by n. Okay, so 1 angle, so you multiply this number by 1 angle minus 2 by n. Do you understand this? Is okay? And now you can do pattern matching. What do you multiply this by? 1 angle minus 3 by n. Okay, multiply this by 1 angle minus 3 by n. And what do you multiply this by?
Why are we considering 2 rotations for next sample? Like figure out the next sample?
Oh, because each of these numbers in the discrete Fourier transform stands for the amplitude and phase of a particular frequency spiral. So this is the 0 frequency spiral, this is the spiral that makes 1 entire turn, 2 entire turns, and so forth.
So we are calculating Fourier transform.
This is the Fourier transform.
I thought you were calculating convolution.
No. Okay? Okay? So how much? So there is a Fourier transform. How much does this number multiply by? 1. And is that intuitive as well? That spiral is just 1, 1, 1, 1, 1, 1, 1. If you shift it, what will happen to it? Nothing will happen to it. So you don't change that spiral. Okay? So this gets multiplied by 1 and so on and so forth. Is this clear? Okay? Okay. So shifting in the time domain or in the signal domain is multiplication in the frequency domain by these numbers here. Okay. Now, of course, we already saw before that shifting is a convolution. And so multiplication by some numbers was going to happen. We just found what those numbers are. Those numbers are nothing but the eigenvalues of the shifting operation. That makes sense? Okay. Right? This operation here, multiplying by these specific numbers, is called twiddling. And though that looks like something I made up, it's there in your textbook. Okay, so just think of these, you have these complex numbers here, and what you are doing is you are changing all of those complex numbers by some rotation. So the first complex number you don't change, second complex number you pull it back by 1 by n, then the next you pull it back as in negative 2 by n, negative 3 by n, negative 4 by n, and so forth. Eventually you have turned an entire circle of twiddles, okay, of angular movements. Okay, that is how you modify the Fourier transform. Okay, so this is, if you want to give this a name, you will call this the shift theorem. Shift theorem, shifting in signal domain equals twiddling in the frequency domain. Okay, and now, can you now easily see what will happen if I were to shift by 2? If I were to shift by 2, what will happen in the frequency domain? Or just twiddle twice. Like rotate and then rotate again. Right? Which is the same thing that you are saying. Right? Just do minus 2 by n, minus 4 by n, minus 6 by n. Okay? It's also instructive to think of this in the bi-infinite signal space. So instead of periodic signals, just think of signals starting at minus infinity going to plus infinity, but still discrete signals. And this signal, let us say, was shifted by one sample. What will happen to its discrete term Fourier transform, the DTFT? Now the DTFT is a continuous thing from minus omega to omega. Sorry, from minus pi to pi or minus half to half, depending on how you are measuring angles, right? But the omega is continuous, and in this continuous omega, you will get a twiddle. Why? Because you can imagine this signal as built up out of those various spirals, and each spiral is going to twiddle back by one angle minus omega. Okay? So that is how the shift theorem will work in DTFTs. Okay. The other two Fourier transforms also you can figure out how shifting will work. Okay. We are going to require this later on, so we'll concentrate formally on this one, but the other ones work similarly. Yeah, you can solve all the four Fourier transform cases and how shifting affects each of them as homework. Okay. We are going to require this later on. The village chief's cow had a calf. Last story of the season. Village chief's cow had a calf. Village chief tells his daughter, go tell everyone in the village, our cow had a calf. It's a celebration in the evening, please come. Okay. I'll draw the village. Village chief tells his daughter, go tell everyone. Okay. So, village chief's daughter starts from village chief's home and goes to every home and starts telling. Now, parallelly, village chief also starts. But village chief is a portly person, you know. Takes his time. Village chief's daughter is going, telling everyone. Okay? This is what happens. Village chief reaches his first neighbor and says, "Hey, my cow had a calf." He sees his daughter entering. The village chief gets angry. "What is this? What are you doing? What did I tell you? Go tell everyone. You're still here. This generation doesn't want to do anything. All you want to do is slack off. How will you become village chief?" Daughter is like, "I didn't say I want to become. What are you doing? You know, when I was young." Okay, daughter said, "Okay, I know that. You didn't have Instagram. I know that." Okay? Village chief said, "Go tell everyone right now." Daughter says, but village chief says, "No buts, no ifs. When we were young, we never spoke back to our elders. Go tell everyone." Daughter says, "Okay, I'll go tell everyone." Daughter starts. Daughter goes. Village chief is a big, old, portly person. Village chief is also going. Daughter is also going. Okay. Village chief says, "You are still here. What is happening? What did I tell you and what you are doing?" Okay, you get the story. The point is that
Should not have circular answer.
Soft skills are important.
soft skills are important. Here's the importance of city planning. Do we have a city planning department in this somewhere? Not yet. Okay. So, like a civic science department or something. When you have one day, I'll be able to say, I taught them as well. Okay. Anyway. So, what is happening is that if you take certain snapshots, okay, and disregard intermediate information, then you cannot sometimes distinguish between certain phenomena and certain other phenomena. Correct? The path of the daughter and the path of the village chief are very distinct from each other. But at certain moments in time, they look the same. Okay? Now, what is the path that the daughter is following? If we anti-clockwise is okay, but if we also thought of it as having a time axis, let's imagine it as having a time axis is coming out of the board towards you. Then what is the path that the daughter is following?
Spiral.
It's a spiral. Correct? It's a spiral. What is the path that the village chief is following? It's a spiral. These are spirals of different frequencies, but they seem the same at certain instants. Okay? This phenomenon has various names. One of the names is aliasing. Aliasing or aliasing, however you want to pronounce it. Okay. Where does the word aliasing coming from? It's
It's a second or an alternate name.
It's an alternate name of what?
Definition.
That's the definition of an alias.
Yeah, I know. But how does it relate to this? That it doesn't know. He's just explaining the dictionary. Okay, do you know the dictionary meaning of the word alias? Alias is second name, is right. Okay. So here what is happening is that the high frequency spiral and the low frequency spiral are indistinguishable from each other if we were to look at it at certain time instants, and so they are aliases of each other. We'll see how that comes about in a minute, okay? But that's where the word comes from, aliasing. Have you ever seen the blades of a fan rotating backwards, seeming to rotate backwards? Why does that happen? The fan is rotating like that. Look at it, you look at it, you look at it, and it starts rotating this way. Did they design it that way? So push some air, then pull some back, otherwise there will be no air to push. No, the fan is actually rotating this way only. We can't keep up with the rotation. We are the village chief. Our brain is the slow village chief and it's going, why are you still here? Something like that is happening actually. How many of you have observed this phenomena somewhere, right? Sometimes you might have seen the wheels of a car or a bus go the wrong direction to the direction the bus seems to be traveling in. And if you have noticed this, why? How is this happening? Okay, so here's something that many of us don't realize, that this kind of phenomenon only happens when there is some kind of chopping up of the time instants. Okay, so for example, if you have seen the wheels of a car or a bus rotate in the wrong direction, you have probably seen it in a movie. Okay, you don't realize it, but you have not seen it in the real world under the sun. Why? Because the sun does not chop up. Sun sees everything. It's an omni-observant fellow. Okay, so it's probably you have seen it in a movie or on the TV or somewhere like that, where you have frames, right? And what happens is the wheel is actually moving this way. Let's say that the wheel has, let's say for simplicity, wheel has 3 spokes. Okay, wheel has 3 spokes, and what happens is you see one frame of the wheel, and then because there are only few frames in your camera is capturing at say 24 frames or 25 frames or 50 frames a second. By the time the camera captures the next frame, your spokes have turned so much that you cannot distinguish between whether this spoke came here or this spoke came here. Okay? And that's why, even though it is rotating like this, you think it's rotating like this. Your eye seems to think it's rotating like this. That's happening because of the chopping up of the camera. Now, fan, if you're seeing it rotating backwards, where is the camera? There is no camera. Did you watch hundreds of reels on Instagram of fans rotating and some of them have started rotating backward? No, you probably saw your own fan rotating backward. Okay, this happened, and again, 10 years from now, I will probably not be able to take this lecture anymore. This happened because there was something called incandescent light. Tube lights. Remember tube lights? Do you remember tube lights? Tube lights, right, are flickering 100 times a second. Okay, our eyes don't see it because it's too fast for us to observe. On the other hand, if something is moving very fast, the tube lights are actually shining light on it at only a few instants. And so if it's rotating this way, you could actually see it rotating backwards because of aliasing. Okay, so what is happening is a high frequency rotation is aliasing onto a lower frequency rotation. Okay, the high frequency rotation is actually the actual phenomenon is distinct from the low frequency rotation, but because of the way it is being sampled, you cannot distinguish between that and a low frequency rotation, just like the village chief couldn't. Okay, aliasing, write this down. Has this ever happened to you? You are pointing a camera at something like this wall, for example, has this pattern on it, right? This pattern of lines. You're pointing a camera at it, but the camera sees a very different pattern. Has that happened to you? And as you move the camera a little bit, the pattern starts flickering. Has this happened to you? This is aliasing. It is the exact same phenomenon. The pattern has a certain frequency in it. Okay. And because of the sampling of the individual pixels of the camera, that pattern, that high frequency pattern is aliasing onto a low frequency pattern because of the discreteness of the pixels of your image. Okay, so there are many real world places where this phenomenon shows up. Sometimes it is called a stroboscope effect. You remember this term? Stroboscope effect. So, the stroboscope is basically a light which flickers at a very high frequency. And a light flickering at a very high frequency can cause these kind of effects, that very high speed oscillations start looking like very slow speed oscillations. That's a stroboscope effect, which is another name for aliasing. There are actually places where people use this beneficially. So, for example, people who study the voice box of humans or animals want to actually capture the image of the voice muscles, voice folds, opening and shutting, moving. But they are moving too fast. They move like 400, 500 times a second. And you cannot actually capture data at those frame rates because the amount of light you will need is so much that you will burn the throat. So you cannot do it. So instead of doing that, what they do is use a stroboscope on purpose, a flickering light. And they alias that high frequency movement onto a slow movement, and they actually capture a very slow moving voice box. Anyway. Think for a moment that you have a signal, and let's say that it's a continuous time signal. Okay, time is continuous for a moment. And that signal is built up out of some spirals. And let me show one spiral. The signal could have multiple spirals. I'll show one spiral. Okay. If you are sampling this signal at specific instances, what does that mean? That you are going to lift values of the signal only at specific moments in time. Okay. And that's what we do, right? That's called sampling, because real world phenomena are continuous, are considered to be continuous in time. We don't know if there is a discrete time resolution of the universe. We haven't found it. So we are assuming universe itself as continuous time. Okay. It's also a philosophical question of whether we will ever find the discrete time of the universe, because we are part of the universe. Anyway, so universe, let us assume as continuous time. But we want to process signals on a computer, so we take certain samples of the signal, right? And we have assumed that there are samples from the first lecture to now. We have assumed that we have signals in samples. Now, where do they come from? They come from us sampling. That's where the word sampling comes from. Sampling the value of the signal at particular instances. So, if I say the signal is sampled at 400 hertz, the sampling rate is 400 hertz, which is 400 times a second. What does that mean? That means that I have picked up 400 values of the signal in 1 second, correct? Okay. Now, if I have done that, I have picked up some of these values, what am I in the danger of having done inadvertently?
Alias the same value again and again.
Alias the same, that's one extreme thing, but yeah, okay, let's do that first then. Alias the same value or pick up the same value again and again. When will that happen?
When the two frequencies sampling rate is equal to period of the...
Correct. When your sampling rate equals the period of a spiral, you will actually just pick up one value of the spiral every time. And that would be bad, because you won't be able to tell whether it's just a flat value or it is something that is turning that fast. Okay? But it doesn't have to be that high a frequency. Even other frequencies will lead to problems, right? It's not that the village chief was just sitting at his home and he sees the daughter after some time and he says, what are you doing? You're doing nothing. Village chief was also moving. So there were two moving spirals which got aliased.
Same period.
Sometimes any sampling rate we choose is going to start aliasing after some samples.
And let's make that precise. But
Same period.
The
Period is same.
period is
Same of both
If
the.
the initial phase is not rational,
if the initial phase is not rational. Okay, look at it this way. There's a spiral and the spiral is going around like this. If I am, so let me say I sample at some moment and it was here, okay? And then I sample again after some moment and the spiral was somewhere else. What speed of spiral would be a dangerous speed?
smaller than the sampling speed. I mean, faster than the sampling.
Faster than the sampling speed? Yes, correct. So he is saying same as the sampling. Oh, you're saying faster than the sampling. Okay. He's saying same as the sampling speed, and that is when it makes an entire turn and then you catch it again and you see it not moving. Correct? Now he is saying faster, which is of course an aliasing problem. It moves an entire circle and then a little bit and then you catch it again. And you won't be able to tell the difference between if it moved this much or it moved only this much. That is an aliasing problem. Anything else? How about slightly slower? How about if it went up to here and you caught it here, but you can't tell whether it moved like this or it moved like this, right? Which is the village chief problem, right? This and this, okay? And so yes, the generalization is anything faster than half is dangerous, okay?
In general, because we are sampling in a discrete manner, there can be aliasing for every sample, right?
Yes.
We can't comment on it.
Yes, so we are just, we can still comment on it. We can comment on things we can't control, we do it all the time. That's how human beings are.
Figure things out properly.
What?
Like, we can't have a calculated basis of figuring out how the aliasing is happening.
We can, and we are moving towards that. In fact, okay, we'll see.
Why do you say only half faster than half? What is the rationale behind half? It's
So who said half?
you said.
If it is like if between two samples it rotates more than half.
So let's say between one sample and the next sample, the next value pick up, it had moved like this. Okay, so what's your problem?
So
It's for error. Check.
We don't know if it's clockwise rotation of more than half or anti-clockwise rotation of less than half.
We don't know if it is clockwise rotation of more than half or anti-clockwise rotation of less than half.
If it is less than half value, then it's same problem, just flipped.
We don't know whether it's clockwise rotation of less than half or anti-clockwise more than half.
Or if multiple rotations.
You pick any value, it's going to be the problem.
Yes.
In the board
I think what
now.
he is trying to say is, if we know for a fact that all of the rotations will be less than half, then we can map, like we will be sure that every frequency we are getting is that
We can't know that, that's what I was saying.
That is,
Whatever value we pick, we don't know actually what's happening.
I'm sorry, I lost what is going on. Like,
Say what is that again?
so if we know for a fact that after one sample, any value which we take will be rotated by less than half in any direction, then we can be sure that there will be no aliasing.
Do you understand this? If we could somehow ensure that no spiral will rotate more than half in the time duration of one sample, then aliasing will never happen. Okay? So if we could somehow ensure that all spirals rotate almost up to half a circle, half a turn, okay? Then there will never be an aliasing problem, right? Because basically what are you saying? Whatever spiral you see, it is the slowest interpretation of that spiral. Okay? Any sampled spiral is the slowest possible spiral, because if you see something that moves here, then moves here, then moves here, then this is slower than this, and this is the one you pick. Okay? So, if we could ensure that every spiral turns less than half a turn per sample, then aliasing will not occur. Okay? Whether we can know that or not is something that he is already worrying about. We'll answer that question in a moment. But we'll answer that question in a moment. Okay? But the statement is that if every spiral in a signal moves less than half a turn per sample of your sampling rate, then there is no aliasing. This is called the Nyquist theorem. Okay? Nyquist was the name of a scientist. He came up with the theorem called the Nyquist. Okay. Now we could come up with some slight another variant of this. For example, if I knew that all spirals rotate counterclockwise, if I knew that, then what could I allow and still be safe? 0 to 1 turn, right? 0 to 2 pi, which is 0 to 1 turn. I could allow all of them and still be safe. Exactly 1 turn or greater than 1 turn, I still cannot allow, because that will still alias to some other spiral. Okay. But now that, I mean, my saying that all spirals should move counterclockwise is not going to be useful in practical scenarios. Why?
Because you don't hold that information, right?
No, that's there's another much more limiting problem in saying that all spirals are moving in one direction.
Because spirals can move in another way.
Because spirals can move in. No, be more specific, man. And we can't control it. It's all coming back. We can't control it. Anything can happen. No. Because real world phenomena use real numbers, and real numbers will always have a positive and a negative spiral representing it. Right? You break up real, it will always have to be conjugate spirals. Correct? We discussed this many times over the lectures. Okay, so real world phenomena will always have positive and negative spirals. So I cannot limit and say that, hey, only have one direction spirals. Now, if I am allowing both direction spirals, then one good way to limit it is to say that my spiral should never turn more than half a turn this way or this way for me to avoid aliasing. Okay? That's Nyquist theorem. Now the problem is, with real world phenomena, they will do whatever they will do. What control do I have over what they will do?
If our observation frequency is something, so we're continuing to get the output signal in the same observation frequency. So it shouldn't really matter if the lower one is faster or not, because the output would still be the same irrespective.
If we are just looking at output, then why do we even care about aliasing? Because values are going to remain the same.
Yeah.
Then aliasing has a
We could just give them a value,
principle itself doesn't.
assume it to be minus 5.
We care about aliasing because we want a relatively truthful representation of the underlying phenomenon that we are sampling. Okay, and aliasing will cause two very distinct phenomena to look very similar, to get represented very similarly. Okay, so something which was a very high frequency squeal might, after aliasing, be indistinguishable from something that is a very low frequency growl. Oh. Okay. Now, if you are trying to distinguish whether you should be scared and run away or you should be scaring this object, and that depends on whether it's squealing or growling, then there will be a failure in your ability to do so because of aliasing. Your tiger aliased onto your Tweety bird. Okay? Right? So now the question is, do we have control over this? Can we have control over this? And the answer to that is that we can have control over this by filtering. Okay. So basically, we will, by filtering, remove frequencies which are faster than the frequencies that we can successfully sample. Okay, so frequencies that move faster than half a turn are frequencies that we will not allow. Okay, now here's the question now. The filtering that I taught you is filtering using convolution. Convolution happens once your signals are sampled.
Like high pass filter.
Is it a high pass filter? Is it a high pass filter though? It is a low pass filter. What we are talking about is a low pass filter. Keep the low frequencies, remove the higher frequencies. Okay? Okay. So now, okay. So we discussed convolution as a discrete time process. But remember, I have always been saying that convolution is not necessarily discrete time. Anything that is linear and shift invariant is a convolution. So there is a continuous time version of convolution. Okay. And this can be implemented using like actual real world instruments which are linear and shift invariant. So then people use real world linear shift invariant objects or instruments like capacitors and resistors and inductors, or like even like mechanical waves, to design filters that will remove these unwanted frequencies before the sampling takes place. Okay? In principle, do you understand what I said? And
Because of
Understanding
the
relatively.
it does defeat the purpose of understanding the signal if you did want to capture the squeal as well, if you want to capture the growl as well as the squeal, now what is happening? The squeal is getting cut off by this kind of a filter that you are using. It's what's called an analog filter, a filter that happens before you are sampling. Okay? But you are cutting off the squeal. So what does that mean? If you do want to capture the squeal, what will you have to do?
Increase the observation frequency.
You will need a filter which has a higher cutoff frequency, which means that you will also need a higher sampling frequency. Okay? So the Nyquist theorem is usually presented in the reverse manner of the manner in which I presented it. Right? Instead of saying that your signals should be not moving more than half a circle, you say the same thing but as a constraint on your sampling frequency. That's just a presentation. The mathematics is the same. You present it as what? What should be your sampling frequency? Your sampling frequency should be such that your fastest spiral turns less than half within that sampling frequency. Do you understand this?
This is like a continuous this thing.
This is a continuous time.
No, it's a what? Like Hydra, you cut off one head and the other thing will grow. So you increase the sampling frequency, and you feel you should increase the. Then you have to capture something else. Then you again increase and never-ending thing.
Yes.
So why do we do this? Why do we care?
It's too philosophical to answer in the next 5 minutes before the break. So.
Naturally occurring spiral frequency. If we do, then it makes sense to keep on increasing sampling rates, right?
Competition.
Isn't that same as asking is physical time discrete?
It is, I think, the same, very similar to asking whether physical time is discrete. Yeah. Quantum physicists have something to say about phenomena with a certain limited age. Energy will not have frequencies higher than something or something like that. And yeah, people will do some kind of approximations of that kind. But you're right, there is this kind of race that, hey, I don't know if I'm missing even higher frequency data. Let me try to capture at even a higher sampling rate. Maybe that's not enough. Let me try to capture at even a sampling rate. And people do find interesting phenomena at higher and higher frequencies. So in general, what you're saying is true. And and there is an edge of what's possible technologically. And we are all, as engineers, we keep pushing that edge. And scientists keep using more and more higher frequency data to understand more and more phenomena.
Wouldn't it be less problematic if we just allowed aliasing to happen?
But then we won't be able to distinguish between certain phenomena and certain other phenomena.
Trade-off.
Can't you come up with a better lower bound than the Nyquist theorem for sampling frequency?
Why? How?
I mean,
Nyquist couldn't. I can't as well. If you can tell me.
the reasoning is because if sampling frequency is just twice, let's just say, then we'll just, and if we are taking a sine wave, then we'll just get a triangle graph. So the question is, there has to be something more to get the sine wave better.
Yeah. Yes, you are right. So, not better, it's actually, yeah. Like, is it even worse than what Nyquist would imagine it to be? And yeah, you are right. And so, there's too much to explain. Something called beating starts happening when you are very close to half. And This has to do with signal reconstruction, which is the opposite of sampling. The question you're asking is about the opposite of sampling, that if I have sampled something, can I really reconstruct it? So mathematically you could, but then practically can you, becomes the question if you want to actually produce the signal out. And that has certain issues, and which is why people usually sample at much higher than what the Nyquist limit says. So, yeah. There is a lot of maths that you can work out, but there is a bit of artistry involved as well. So, just to give you that. So sometime in the 1960s, someone came out with a paper in audiology saying that humans cannot hear higher than 22.05 hertz. 22.05 kilohertz. That makes it better. 22.05 kilohertz. Okay. How did I measure it this precisely? It's odd. But someone came up with a paper like that. हमने 100 लोगों से पूछा. No one could hear higher than 22.05 hertz. And so 22.05 hertz is the limit of what humans can hear. And so if 22.05 hertz, you cannot hear higher than that, then what would be the Nyquist sampling frequency that you will need? Double of that, right? Because this 22.05 spiral shouldn't turn more than half. Okay, so the simple thing is that whatever frequency you have in your signal, you need double that as the sampling rate. Okay, and technologically that was barely feasible. Okay, the samplers till then were like 8 kilohertz or something in the 1960s. And so then engineers worked hard and finally reached this, and everyone said, oh, full spectrum. They call it hi-fi, high fidelity. Okay, this will produce the same output that the actual world produces. It's indistinguishable. Okay, 44.1 kilohertz. Then what you said started happening. They said, no, that's not enough. Then it went to 48 kilohertz. Then they said, that's not enough. Then it went to 96 kilohertz. Then now they're saying, yeah, that's not enough, and they're going to even higher frequencies. So, yes.
At higher and higher frequencies.
Yeah, microprocessor is not the only problem. The actual sampling and the filtering itself is also a problem. The pickup, the microphones and all of that is also a problem. Anyway, okay? Okay, this is all just time pass for fun. Shall I go ahead? Yes. Yes.
So, like you said that in no physical situation you would have only only one direction rotation, right? So, like I was thinking about like polarized electromagnetic waves. Won't they technically have only one direction?
Yes. So there are actually certain situations where actual complex signals show up. Polarized electromagnetic waves can be expressed using this theory, but using complex numbers. It's called Jones calculus. Look it up. Okay. Okay. Another place where it shows up is what is called epicyclic theory of the rotation of planets. These are the two places I know that actual complex number modeling, spirals without conjugate spirals will show up. These are the only two places I know. And you correctly pointed out one of them. Good. Okay. Now, suppose I have a sampled signal. Okay. Suppose I already have a signal that is sampled. And I decide that, oh, this is too much data for me to process. I don't want to process all of this data. Let me subsample this. Okay, let me take only, let us say, every alternate sample. What danger will that produce? That will produce aliasing as a danger, right? So even if in the original sampling itself, I had correctly taken care of aliasing, now the subsampling again leads me to the danger of aliasing. Do you understand this? Now this is something that I can analyze entirely in the discrete signal space. Correct? So if I have a signal and I choose to only keep every alternate sample. So I'm keeping this, I'm keeping this, I'm keeping this, but the other samples I'm losing out. Okay? This is called subsampling, right? Sampling, subsampling. What will happen? This will create new aliases, right? Things that were earlier distinguishable now will start colliding on each other. Spirals which were earlier distinguishable when you had all of this information might now start colliding with each other. Can you point out two spirals which were earlier distinguishable but are now aliasing, now colliding on each other? 1/4 and
Half-fling.
1/3 and 1/6. The half rotation and full rotation.
half rotation and full rotation. That's one. That's wait. There's no full rotation, right? There is rotation. Spirals are rotating.
Spiral which has period of the sample and spiral which has period of half the sample.
Spiral at which sample?
No, the entire whatever period we have right now.
Okay, white sample or blue sample? Spiral which has the period of the white sample has already been cut out by Nyquist. So that is something that we are not worrying about, right? So which are the two spirals which were distinguishable to the white sampling and are not distinguishable to the blue sampling period?
n-1 and n-3. n-1 and n-3.
No, this is happening this is by infinite. So let's use the omega, like DTFT kind of calculus here.
Half and 1/4 of the period. The period is becoming half when we go from white to.
Be careful. You have to show me four things. You have to show me two frequencies which are distinguishable to the white sampling rate, and when they go to the blue sampling rate, they start looking the same. This is what you have to show me. You are saying some numbers. You have to show me something like this. Two frequencies which are distinguishable to the white sampling rate, high sampling rate, and become indistinguishable when you go to the blue sampling rate. What is 0 and 1? Okay. Constant and up down. Which two boxes are you filling? The white boxes. Okay. So something that makes 0 turns per sample and something that makes half a turn per sample. Okay. Something that makes 0 turns per sample and something that makes half a turn per sample, right? So one spiral goes 1, 1, 1, 1, 1, 1. Another spiral goes 1, -1, 1, -1, 1, -1. But where the blue samples are concerned, they look the same. They both look 1. They both look 1. They both look 1. Okay? So you cannot distinguish. They both look like the 0 spiral. Because 0 spiral becomes 0 spiral. Half spiral, the one that makes half a turn, becomes what? When you halve the sampling rate, it now makes one entire turn. But one turn is indistinguishable from 0 turns. And so this is actually 1, but looks the same as 0. Okay? Any other example?
Signal which goes like in the white thing as 1, 2, 3, 4, 1, 2, 3, 4
Okay.
is indistinguishable to the blue one to a signal which goes 1, 1, 3, 3, 1, 1, 3, 3.
Correct. But these are not spirals. You are right. But we want answers in terms of spirals. So these are nice two signals which are undistinguishable, but they are not spirals. Yes. Okay. So
One half.
1/2, 1/2.
As in comes
The
from
signal.
0 turn, goes to half, then goes back to 0. And ulta direction.
And ulta direction is actually the same spiral even for the white.
1/3 and -1/6.
1/3 and nice. So 1/3 and -1/6. Okay. I'm saying nice. Let's see if it's actually nice. You start from here and you go 1/3. Sorry, I didn't draw the 1/3 very well. (1/3) and (-1/6) are the two spirals. Okay. So this goes (-1/3). Where will it be after two samples? Sorry, not -1, +1/3. Sorry, my mistake. 1/3. Where will it be after two samples? 2/3. It will be here. (-1/6). Where will it be after two samples? (-2/6), which is (-1/3), but that's indistinguishable. Okay. Did you get that? So this is a nice example. Okay. So 1/3 becomes 2/3 and (-1/6) becomes (-1/3). But 2/3 and (-1/3) are indistinguishable. So these two things aliased onto each other. Okay. In general, what will happen is opposing spirals will alias onto each other. Okay, why? Because they start together, then whatever do they oppose, then they come back together, then they oppose, then they come back together, then they oppose, then they come back together. Okay? So, in the DTFT,
This is true only for subsampling is for alternate samples.
this is true only if we are subsampling every alternate sample. Okay? And I invite you to extend this theory to every third sample, every fourth sample, or such generalizations. Okay? And but it's easy. It's easy. Okay. So (-1/2 to 1/2. Okay. So what happened? This fellow 1/3 is indistinguishable from this fellow minus 1 by 6 when subsampled. On this diagram, which is the DTFT corresponding to the white sampling rate, they are distinguishable. This frequency is here, this frequency is here. This is the DTFT. Okay? Okay? And when we subsample, this and this will become indistinguishable. Okay? Similarly, this, what was the earlier example? The 0 frequency 1 1 1 1 1 and the half tone frequency 1 minus 1 1 minus 1, which are these two. Okay? So in general, and work it out precisely, I have given you enough information to work it out precisely. Anything that is a jump of half aliases when you subsample. Okay? Now, what is a good way to avoid aliasing? You will have to cut out some more frequencies, by the way. There's no way to keep all the frequencies and not have aliasing. If we were to go in a similar fashion to the Nyquist thing, that okay, let's keep the lower frequencies among the aliases. Among aliases, always keep the lower frequencies. What are the frequencies that we are keeping and what are the frequencies that we are letting go?
Can we sample at an angle from
No. Yes, there are theories like that, but that's too advanced for right now.
But that would solve these issues.
No. It will present more issues that it will solve right now. Chalo. Tell me. What frequencies will you keep? Minus 1 by 4 to 1 by 4. That's intuitive also. That's correct also. Minus 1 by 4 to 1 by 4 are the frequencies that you keep. Why? Because the alias of this fellow is always half away, which means it's just outside that other fellow. Okay? So alias is always outside. Alias is always this. Where is this fellow's alias? Here. Okay? Which is the same as this, by the way. Okay? Because this is also a circular domain. Okay? Here. So the alias is always outside. Alias is always outside. So if I had frequencies which were just between minus 1/4 and 1/4 instead of minus half and half, then we will not have to worry about aliasing. And how do we ensure that frequencies are always within this? By filtering out the other frequencies. Okay? Which means that you design a filter that will keep these lower frequencies, and remove the higher frequencies. Okay? So this is the Bode plot of the filter that you want to design. Okay, Bode plot or DTFT of the filter that you want to design. Correct? Correct. This, by the way, this it has got a name to it. This is called a brick wall, filter, because it kind of looks like one brick in a wall, the rest of the wall is yet to be built. But someone called it the brick wall filter. Again, this is in some textbooks at least, the brick wall filter. The ideal filter that keeps only those frequencies, remove the other frequencies. Okay? Now, how will you design this filter? If you want, what is a filter? A filter is after all a convolution rule, right? So what is the convolution rule itself? What is the spreading rule? What are the spreading multipliers? What is the impulse response?
The inverse.
Yeah, you take the inverse DTFT of this, take the inverse discrete time Fourier transform of this thing, and whatever are the numbers, those numbers are the filter coefficients of your brick wall filter. And so the ideal subsampling methodology is taking those numbers, you can calculate it, they turn out to be some numbers. It's called the sinc function. Okay. So the ideal thing is to take this filter, take its time domain representation, use that as a convolution filter, convolve your original signal, white signal, that will cut off some frequencies, which means it will smoothen the signal to such an extent that if we now subsample it to every alternate sample, you will not get higher frequencies and lower frequencies aliasing on top of each other. Of course, now the exact brick wall filter has infinitely many coefficients. It's an infinite impulse response filter, but it's not an ARMA filter. So it's got an infinite impulse response, but it doesn't have a finite calculation structure either. So you can't actually use it. So you have to use approximations of it, and the approximations do not have that very perfect shape. And so then it goes into a lot of heuristic methods of, okay, what do I do and how do I design good subsampling and so forth. Okay. So this is the theory of subsampling.
This is a very weird way of dealing with aliasing. It's like saying you have a heart problem, so I'll remove your heart.
If your heart is here, don't subsample, please. If your heart is within, if you know that your heart is, see, many times you are subsampling because your original sampling or your original sampling rate is decided by whatever is the hardware that you used.
No, subsampling part is okay. The Nyquist way of taking on the half turn signals. So we are preventing aliasing by just cutting off half of frequency or cutting off a lot of frequency.
Correct.
So it's losing so much information.
Correct. Yes, that's the only way we know. It's the same thing, right? Going back to that same question. So yes, you're right. You're losing a lot of information. Correct.
And we haven't really prevented aliasing. We have just killed signal to what it was.
We have prevented aliasing by just killing off one of the things that could cause aliasing, and that there could be useful information there which we are losing out. Yes. But we get it now. You have been saying it. I agree with you entirely. So we can't help it. Okay. At least I can't help it. I don't know any theoretician who has been able to help it yet. So sorry. Maybe one day you can.
It's a good way of doing it.
No, but it's the only way
It might be the best we can do, but
I don't know anything better. Okay, let's take a short break. We'll see a very nice positive use of aliasing. 5-minute break, please.
did Nyquist also get these comments that you have done this?
No, Nyquist was sitting in one corner of the world. He never talked to anyone. He just published a paper. He was saved from all the negative feedback on his theory. The opposite of subsampling is called supersampling. And I am going to try to quickly introduce the theory of supersampling. It is basically that you have a certain signal and you want to have a signal at a higher sampling rate. Okay. And let's say that sampling rate is exactly double the sampling rate. Okay, which means in reverse of what you did before, you want to now add samples. Okay, so how do you do it? And you can come up with various practical ideas, right? Like, I mean, how do I introduce a new sample here? Maybe I could just repeat the previous sample. Okay, that's one idea. Or you could maybe average the two samples. That's one idea. Okay, now there is one like theoretically perfect idea, and I'll discuss it in brief. The theoretically perfect idea starts by doing something very strange. You add to the original signal, you add samples, alternate samples with the value 0. Okay. Now it turns out that if you know the Fourier transform, let's think by infinite, so it is the DTFT for the time being. If you know the discrete term Fourier transform of the original white signal, then this 0 added signal also has a Fourier transform that can be calculated from the original Fourier transform. Okay. And so if the original signal had some Fourier transform, when you add these 0 samples, what will happen is, well, two things will happen. Think about it. First of all, the frequency names will change. For example, something that was, let's say, making quarter a turn in the white samples will now make how much of a turn? 1/8 of a turn. Okay, something that was making quarter of a turn will now make 1/8 of a turn. So the amplitude and the phase of the quarter turn spiral of the white signal will become the amplitude and phase of the 1/8 turn spiral in the supersampled signal, in the new signal, correct? And so what happens is something that was, say, here 1/4 will now get here 1/8. Okay. So as you add these 0 samples, what is happening to your frequency content? Do you see that? That frequency content now looks the same. It's that same figure, but everything from -half to half is crunched down to -1/4 to 1/4. But that's not all. Something else that is surprising happens. Okay. Look at it. So think of at the higher sampling frequency, the 1/8 spiral. Okay. 0 angle, 1/8 angle, 1/4 angle, 3/8 angle, half an angle, and so forth. Correct? Half a turn, I mean. Okay? Yes? There is another spiral which is the -3/8 spiral. Where will it be here? 0. Then here it goes to -3/8. Here it goes to -3/4, but that is 1/4. Okay. Then it goes somewhere, then here it will go to half. So where the non-zero spirals, non-zero numbers occur, it is the -3/8 spiral is indistinguishable from the 1/8 spiral. Do you see that? Now, how do you actually take the Fourier transform? You take the Fourier transform by taking dot product, correct? So the dot product of the 1/8 spiral and the minus 3/8 spiral will be the same, and also be the same as the dot product of the 1/4 spiral for the original signal. Okay, so what happens is this 1/4, this number here becomes this number for 1/8 here, and also the same number will also show up at minus 3/8. Okay, so when you put in the zeros, you get that same, the frequency domain content will shrink and come between minus 1/4 and 1/4, and another copy of that will also show up on the other side. Do you see that? This is aliasing. Correct? Basically, it's a slower spiral and a higher spiral seeming the same at the non-zero numbers. Okay? And so what will happen is that this same shape will show up 2 times when you put in those zeros. Okay? It's like creating aliases. Now, what do you actually want to happen? You are assuming that the original 1/4 spiral is actually a 1/4 spiral, not an aliased faster spiral. Correct? Which means that you want it to show up at the 1/8 spiral and don't want to show it at the minus 3/8 spiral. What do you want at the minus 3/8 spiral? Nothing. You are super sampling. There should be no information at the higher frequencies. Right? Like if you zoom into a low resolution image, you should just see a smudge because there is no high resolution information there. Same thing, right? And so now what do you do to this? Filter. Correct? Take this and use a brick wall filter to keep the low frequency content and remove the high frequency content. The brick wall filter is the same brick wall filter that you use for subsampling. Okay, it's the same minus half to half brick wall filter. And you add these zeros and then you convolve that whole signal by that brick wall filter or whatever realistic filter you can design which has got a similar shape, and that is super sampling. Okay? And I will show you a very interesting use of super sampling. This is our last topic, but it's going to be a little longish. Today is the last day I can teach you, so no, not that longish. Okay, my last part of the theory is going to be in the finite discrete domain or the discrete domain, which is the Fourier transform or the discrete Fourier transform domain. Okay. So let's say you have a signal which is finite extent. So let's just have some numbers: 2, 1, 3, 2, minus 1, 4, 8, 6. Okay. And it's finite or it's periodic, which means it goes around in a circle. Okay. If I want to calculate its Fourier transform, its discrete Fourier transform, the DFT, the way I have taught you till now, what will I have to do? I will have to take the dot product with every sample. Okay. How many dot products will I need? 8 or n dot products. Correct? How much effort does it? Let's just calculate multiplication. How many multiplications does it take for every dot product? N. So the total number of multiplications I will take is n square. Is that correct? Right? To calculate the Fourier transform, I am going to take n square multiplications. Correct? Remember this fact or write it down. Now, I am going to do the following trick. I am going to calculate the Fourier transform of this signal 2 0 3 0 minus 1 0 8 0. Okay. And I am going to separately calculate the Fourier transform of this signal 0 1 0 2 0 4 0 6. Okay. I am going to calculate the Fourier transform of these two signals. If I calculated separately the Fourier transform of these two signals, from them will I be able to calculate the Fourier transform of this signal? By? No, you don't have to eliminate the 0. These two signals added up give this, right? And so what happens to the Fourier transforms? They're just a bunch of dot products. Dot products are linear, which means that if you add up just frequency wise, add up the numbers in the two Fourier transforms, you get the Fourier transform for this. Okay. This in itself is still not very interesting. The interesting part comes in a moment. Do you understand this? I had 8 numbers and I just like pulled them apart into two separate signals, which if I add them back together, I get the original signal. Now, to calculate this 2 0 3 0 minus 1 0 8 0, what's the trick?
Half it.
Again, some subsampling. Again, half it.
Yeah, just okay. Just calculate the Fourier transform of 2 3 minus 1 8. Okay? Huh?
What is that?
2 3 minus 1 8. It's just this without the zeros. Okay? Which is basically just every alternate number here. Okay? So, I separated the two signals and I squished out the zeros. So now I have only 4 numbers here. Okay? Or n by 2 numbers in general. Okay? Is okay? If I calculated the Fourier transform of this, somehow I want to create the Fourier transform of this from this Fourier transform. Divide the frequency by 2 is correct, and then something else.
The rectangular filter.
We did that
Before the filter, we just use to eliminate the higher frequency.
we will get higher.
So don't eliminate, keep them. Okay. This is because you want to go to this signal, you don't want to smoothen it out.
We have to add the higher frequency.
Correct. Just use the aliases. Right? Do you understand this? So, I'll do this precisely in a moment. So, but just roughly, first to give you an idea of what happens is, you take this 2, 3, minus 1, 8. You take the Fourier transform of this. Okay? Take the Fourier transform of this. And then, from that, you calculate the Fourier transform of the zero space signal quickly. How? By what I showed you just a little while ago. Right? Of basically what happens to the Fourier domain when you add zeros. You just get a duplicate in the Fourier domain. Right? You saw that a minute ago, right? You got two versions of the same thing. We'll see this precisely in a moment. Okay? So that will quickly give you the Fourier transform of this. Okay? Similarly, you will take what? You will take the Fourier transform of this 1, 2, 4, 6. Okay? 1, 2, 4, 6. Which is what? Which is this signal. Now from 1 to 4, if you have the Fourier transform of this 1, 2, 4, 6, how will you get the Fourier transform of this?
Just anything. But now 0 is first.
Now 0 is first. So
So I have to add on either this side or that side in particular.
Add
It's just
1 by n.
shifted by 1.
Minus 1 by n. Well, in the phase
Twiddling,
you need to
twiddling.
multiply.
twiddle. Yes. Yes. So you do two things. You do a duplication by doing this 10, 20, 40, 60, right? Going from here to here, just by duplicating the Fourier transform. We'll see this in detail in a moment. And then go from here to here by twiddling, because it's a shift. Okay? And this seems like a very complicated thing to do. Let's see what we have achieved. Now, these two Fourier transforms are n by 2, correct? How much effort will it, now let's say I calculated the Fourier transform here, straightforward manner. How much effort will it take? N square by 4. This effort will be n square by 4. Together the effort is n square by 2. Okay? The extra effort here is a few copies and a twiddle, which is like 3 times n. But it's nothing like the other n square by 2. Okay? So instead of n, we got n square by 2 plus a little bit. Sorry, instead of n square, we got n square by 2, n square by 4 plus n square by 4 plus 3 times n. Okay? And so that's faster. But then what do? You don't do this Fourier transform in a straightforward manner either. Now you have those, you will separate them out into this and those, and go on doing that for as many levels as you need. Okay? And that is the fastest way of doing it. That's called the fast Fourier transform. I'll show you the precise theory in a minute. It will not take a long time. But do you understand the structure of the method? Yes?
The shortest amount of multiplication that you would do is 2n. Or
Is what?
is it 2n, the shortest amount of multiplication that you could do? So we started off with n square. Then by
So I haven't analyzed that yet. We got n square by 2 plus some n. But then those again now are being done using the same methodology of separation. We haven't calculated how fast we got yet. We'll do that. So let's see this precisely. Okay. 2, 3, minus 1, 8 is that signal, and 2, 0, 3, 0, minus 1, 0, 8, 0 is this signal. Correct? We want to go from the Fourier transform of this signal to the Fourier transform of this signal. Okay? Okay. Now, Fourier transform is a bunch of dot products, right? What is one of the spirals? One of the spirals is just the k equal to 0 spiral. Correct? Yes? So, let's look at k equal to 0 spiral. 2, 3, minus 1, 8. What is the spiral? Numbers? 1, 1, 1, 1. Correct? Yes? Now, which spiral here will produce the same numbers? Will produce the same dot product? No. Which spiral here will produce the same numbers? 1, 1, 1, 1, 1, 1, 1, 1. Which is k equal to 0. Okay. So, k equal to 0 spiral here will produce the same numbers. But there is another spiral which will also produce the same numbers. K equal to? Now k is in index. K is already an index. So, what do you say? Is it n by 2? Yeah, n by 2. Correct. You're right. Yes. So, the spiral is 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Dot product will be the same because these zeros disregard the minus 1. Correct? Yes? Where it matters, that spiral is an alias of the earlier spiral. The fast Fourier transform is just a beneficial utilization of aliasing. Okay? And so, k equal to, what is it? So, k equal to n by 2, let's just use, there are 8 numbers, so let's just be specific here. This is k equal to what? 4, 0, 1, 4, right? 4. K equal to 4. Okay? There are k equal to 0 to k equal to 7 spirals in the 8 sample Fourier transform. Okay? Now, the next spiral is k equal to 1, which is the spiral that makes 1/4 of a turn. Correct? Right? This is the 4 sample domain. This is the 8 sample domain. So, this k equal to 1 makes 1/4 of a turn. So, it goes 1 I minus 1 minus I. What is the spiral here that will have the same numbers where it matters? The spiral that makes 1/8 of a turn. Correct? And what is the index of that spiral? 1. Correct? So, k equal to 1, the same numbers will be seen in k equal to 1, but also minus 3/8 of a turn. Correct? Correct. No, minus 3/8 of a turn. And that is what k equal to 5. Right? Because when doing discrete, we call it spiral number 5 just by convention. Okay? Minus 3/8 or 5/8, we call it spiral number 5. So, k equal to 5. Okay? The next k equal to 2 is 1 minus 1, 1 minus 1. And one of the spirals it will alias onto will be 1 I minus 1 minus I, 1 I minus 1 minus I, which is what? Which is 2/8 of a turn. So, that is k equal to 2 spiral. And 1 minus I minus 1 I, 1 minus I minus 1 I, which is going to be the k equal to 6 spiral. Okay. And k equal to 3 will behave similarly, similar to k equal to 1, and it will produce numbers in k equal to 3 and k equal to 7. Okay. So, you calculate the Fourier transform of this, and that gives you these 4 numbers, and all you do is just write down those same numbers 2 times. Okay? You understand this? Whatever, this gives you 4 numbers, 4 complex numbers as the Fourier transform. All you have to do is just write those numbers 2 times, and you get the Fourier transform of this. It's as trivial as that. Do you understand this? Same thing. So, if you have this 1, 2, 4, 6, you do 1, 0, 2, 0, 4, 0, 6, 0. How do you, if you have the Fourier transform of this, how do you get the Fourier transform of that? Just take the Fourier transform of that and just write those numbers 2 times. Those complex numbers, write them 2 times. You get the Fourier transform of 10, 20, 40, 60. And how do you get to the Fourier transform of this? Twiddle. Right? You just multiply the first number by nothing, the second number by 1 angle minus 1 by n, the next number by 1 angle minus 2 by n, 1 angle minus 3 by n, and so forth. Okay? In the fast Fourier transform, these are called twiddle factors. Factors that help you twiddle. Okay? Right. So, in general, all you had to do was a bunch of copying, and one twiddling is 1 multiplication. So, n multiplications. Okay? And from these, you were able to get to this. Let's just count multiplications for the sake of simplicity. You got from these 2 to here using n multiplications, correct? So let's just see what happens in general, right? You have this 2, 1, 3, 2, minus 1, 4, 8, 6, and you broke it up into these 2, 2, 3, minus 1, 8, and 1, 2, 4, 6, and then using just n multiplications, you went from here to here. Now, what will you do further? You will break it up into 2 minus 1 and 3, 8, correct? And you will break this up into 1, 4 and 2, 6, correct? Now, going from here to here, you will require how many multiplications? N by 2. Yes? N by 2 for this part. Going from here to here, you will require how many multiplications? N by 2. So, in general, going from this level to this level will require how many multiplications? N multiplications. Okay. Now, the same thing, you know, you are going to require n multiplications for every level that you go. And how many levels are there?
n minus.
Log n.
Log n to the base 2. Okay. This, by the way, this easily works only for powers of 2. N being powers of 2. You can make it work for other things as well, but you have to work hard for that. Okay. So then, every level has n multiplication. There are log n to the base 2 levels. How many multiplications? N times log of n to the base 2, which is much, much faster than n square. Especially imagine if you are doing this for 1024, 2048 or this number of samples. 1000 into 1000 is much bigger than 1000 into 10, right? So it's 100 times faster. The fast Fourier transform is 100 times faster than just doing the Fourier transform itself. This is like, it's so surprising, right? You wouldn't imagine that something can do dot products faster than the dot product can do dot product. But it seems it can. Okay. we beneficially used the supersampling concept or the aliasing concept in a very funny, strange, weird fashion. So, I had introduced this previously, but let's discuss that to some level of detail. Having a faster Fourier transform means that you can actually do faster convolution. It's very surprising, but you can do convolution faster than convolution itself. Okay. Why? Because convolution in general will take, I mean, what did we think? That convolution will take how many multiplications? The number of samples in the signal, each will have to be multiplied by as many as numbers that you have in your convolution. There's no faster way than that. But now, you can actually take the Fourier transform of the signal, take the Fourier transform of the convolution impulse response, okay, using the fast Fourier transform methodology, and then you just have to do multiplications. Okay? Right? And that gives you a final outcome, and you take the inverse Fourier transform of that,
Which is again FFT.
which by duality can also be done using the fast Fourier transform, because the inverse Fourier transform is just the Fourier transform. Okay? And so, you can actually do convolution much faster than running the sigma convolution itself by using the fast Fourier transform. That's, I don't know, it's like, it's almost stunning, right? I mean, it's close to unimaginable that this is possible, but it is. People have come up with lots of generalized extensions of this theory about, how this is happening, and is there like a generalized mathematics, and people extended it into group theory, extended it into various kinds of geometric theories and algebraic theories and so forth. So, many people have lots of thoughts about what is the fundamental underlying mathematical structure which is giving rise to this faster behavior. Okay. Anyway, we can't go there. Quick question. If you have a quick question, yes. Anyone? Yes.
So in that case, we initially had a signal like 8-dimensional signal. 8-dimensional signal, 8-dimensional vector.
Yes.
Now we broke it up into two 4-dimensional vectors.
Yes.
So there is loss of information in this geometric interpretation. So how does this make sense?
But because we broke it up into two such signals, right? So eventually there is no loss of it.
Two 4-dimensional vectors.
Yeah, but there's two of them. So you didn't lose information because you have two of them.
So if you are saying that it is like linear and we can add them, so two 4-dimensional vectors adding will give rise to a 4-dimensional vector, right?
Yes. So which is why you're not adding, you're doing all sorts of strange manipulations while going back. So yes, I mean, yes, what you're saying is true, and it requires a little bit of working through that, going from here through this network that I have shown you of those zeros. We never actually add the zeros, so that's just for me to tell you what's happening. Okay, but these zeros and then the shifting and putting it back is actually a linear network that does not lose any information, is something that you have to work through precisely. But that is the case. Okay. So there are actually practical methodologies of using this in practical situations. Let me end with practical considerations of using the fast Fourier transform for convolution. Chapter number 7, verse number 8 or whatever. No, today is the last lecture. We can't till I have finished my syllabus. No, practical consideration. You can sleep. You can watch it in the video. This is simple if you pay attention. If you don't pay attention, it's even simpler because then I'll go at full speed. Okay. So one practical consideration is that the fast Fourier transform cannot be used for extremely large signal sizes. Okay. So that is, in fact, no Fourier transform can be used for extremely large signal sizes because the dot products have calculational noise and they start losing information. So no one takes Fourier transforms of 1,000,000 samples, for example. Okay. 1,000 samples, 2,000 samples, 10,000 samples, people will take Fourier transform. People will not take Fourier transform of 1,000,000 samples at a time. Okay. Quite often, on the other hand, you have signals which, because they are recordings of sound or something, which easily have million or millions of samples. Okay. Seismic recordings, audio recordings, something like that. Now, if you have that signal, if you have a convolution that you want to apply, the question is, can you use a fast Fourier transform even though you can't actually take a fast Fourier transform of that big signal? How will you do it?
Break it apart.
The simple idea is to break it apart into sizable chunks. Let us say that, 1024 size chunks you are breaking it up into. Okay. So you break it up into 1024 size chunks and you do the fast Fourier transform kind of convolution for each one of them. There's a slight problem when you do that.
We don't get
The
the
edges.
larger
From
The
getting the
edges.
period.
The edges.
The edges. Okay. So what will actually happen? You will get this convolution, but remember you are using the fast Fourier transform is a discrete Fourier transform, which means it is circular convolution that you are calculating, which means what will happen is these numbers will actually go around the edges and affect this part of your signal. Whereas if you are doing a straight convolution, you want these numbers to affect this part of the signal, correct? If you are doing a straight convolution. So what happens is most of your signal, right, except for this, let us say this has got 6 non-zero numbers, okay, just for the sake of some calculation. 6 non-zero numbers. These first 6 numbers here will be wrong. All the other numbers will be correct. Because it's the 6 numbers that go around. Other numbers are working correctly. Okay. So then how do you solve this slight problem of this mistake?
overlap.
Correct. Right? So you shift the window not by 1024 samples, but 1018 samples. You just drop this and calculate it in the previous window. Okay. And then next time you will take this window and you will have to drop the first 6 numbers again. Okay. So this is called the overlap save method. Overlap save method of calculating straight convolution using circular convolutions. And then the circular convolutions are done very fast using the fast Fourier transform. And so this is like a methodology of doing filtering much faster than applying the whole filter in a convolutional manner. Okay. Another trick is, okay, which numbers here cause this problem here? And they were these numbers here, correct? So if I just replace these numbers with zeros, then what will happen? No, sorry. What happened?
We'll have to take those in the next overlap. We'll still have
If we replace these numbers with zeros, we'll get the correct numbers here. We'll get the correct numbers here, yes, except for they will still not account for the effect from here. Okay. So then that trick is that again you are doing an overlap window, but then you are using zeros and then you are adding the overlaps. Not rejecting the overlaps, but adding the overlaps. And that's called a overlap add method of calculating straight convolution using circular convolution.
What if we had zeros on the other side also?
Yeah, you can do that as well. There are 100 such tricks and libraries and libraries of tricks of doing this. Okay, so yeah. And even the fast Fourier transform. Can you do a fast Fourier transform of 18 numbers? It's not a power of 2 and so forth. Lots and lots of tricks. Okay. So this final lecture, we studied the idea of aliasing, which is more than one spirals looking the same when sampled in a particular manner. And we saw at least 4 of its uses. One was in sampling itself, which is the Nyquist theorem. Second was in subsampling and how to correctly do subsampling of signal. Third was in supersampling and what is the perfect way to do supersampling. And fourth was in calculating the Fourier transform in a fast manner, which is the fast Fourier transform, and then that can be used to do convolution in a fast manner. Okay. So I have taught you a lot of stuff. I have, believe it or not, we have gone through those books almost entirely. Okay. It might seem that I teach non-linearly, that, I teach too slowly and then teach very fast. But what you gain is not information, because the information is there in the book. If you understood most of what I said when I was speaking fast, what you really gained was the ability to understand fast. Okay? So remember this, the reason to be in a classroom or even be by yourself. Hey, hello, welcome. We are just starting, please come. So as I was saying, hopefully so the reason we go slow is because we need to soak things. The idea is not to transfer information. Information is always there. The idea is to create concepts and intuitions in your mind. With that soaking into a sponge, eventually allows you to take large steps and leaps, which you cannot if you are lost in the, in the forest of sigmas and notations. Okay? Right? That doesn't mean those things are useless, but the intuition is what then helps you derive and understand those things. I've also tried to make sure that once we understand things intuitively, you have the capability to convert it into precise mathematics. But you are all scientists. Tomorrow you are going to create your own mathematics. If you don't learn this process, you will only be information gatherers. Right? So that hopefully was one of my goals, to help you understand this process of slowing down, getting a feel for things, which allows you to see further. You are answering almost correctly to the end of the lecture. That means you see further. You don't get lost. Believe me, you won't see as much as you see if all you knew was is sigmas and, changing their indices. We do that, and that's important. But that's not the only thing that is there. That's not where the core theory comes from. That's something I hope you take. And of course, something more important from the point of view of the lecture series itself. If you forget everything else, I hope you remember spirals are important. First, convolution is important. Okay, why is it important? Because linearity and shift invariance is everywhere. So convolution is everywhere. So convolution is important. One of the most important things you will encounter everywhere, called by 100 different names. And that means convolutions which are analyzed by spirals makes those spirals important. What we call spirals, people call it the Fourier transform, the Laplace transform, the Z transform, they call it phasors, they call it the, what do they call it? CF, complementary function, right? Complementary function, Fourier transform. Okay? They call it block waves, they call it the H model of transistors, they give it 100 different names. Everywhere you see e raised to I something, it's the same thing. It's a Fourier transform inside there. Okay? So, hopefully, you will remember that gist, that convolution means what? That spirals become spirals. And there's a whole eigenvalue thing, eigenvalue analysis that goes behind it, which allows you to analyze these kinds of structures in a much better manner. Okay? So, thank you very much for attending the lecture series. I hope you enjoyed it and good luck.